Hey guys, this is Srini. Welcome back, and in this video let's actually talk about something that quite a few of you actually requested, which is multi-class unit segmentation. And I did put in a lot of effort into actually putting this together, and in fact every one of my video they may be 15-20 minutes to 30 minutes, but it does take quite a few hours, if not days, for me to actually compile this type of material. So I only ask you for two things. Please like these videos if you like them, and please subscribe to this channel so you get notified when these videos are uploaded. Okay, now in our videos 204 and 205 we did talk about unit for binary segmentation, right? In fact, if you Google search online, most of the examples you find are going to be binary segmentation, binary semantic segmentation. So in the past, like in videos 204 and 205, we looked at electron microscope images and with mitochondria in them, and then we segmented mitochondria against a very busy background. Now, actually doing multi-class semantic segmentation is very easy if you know the original concept of unit, because we just need to tweak a couple of things, in the model, and we just need to focus a bit more in terms of getting our masks or labels ready in the right format, because this is multi-class, right? So let's jump in to understand exactly what they are, and I'll share the code as usual. So please look at the link to my GitHub page down in the description. Now, first of all, what do we mean by multi-class, right? I mean, if you look at any of these images, you see multiple things going on, and I would like to separate or segment each of these. I'd like to segment this darkish area, which is pores in this example, and this grayish area, which is mineral number 1, and this bright region, which is a heavier mineral. And I'm not sure if it's very clear on your side, but if you look at right here, I'm not sure if it's clear from the video, but if you look at this busy clustery area, I mean this darkish area, this is actually another mineral. This is a clay mineral in this image. In fact, this data set is a 3D volume. So in the next video, let's actually talk about, okay, now you segment this for multi-class. How do you segment large images and also 3D volumes by applying this to slice by slice? Okay, I'm not going to talk about 3D unit because I don't have resources, to run those. But for now, let's just focus on multi-class unit segmentation. Now, I've already ran this once just to show you, because I don't want to waste your time running it live. Of course, you can do this yourself. I just want to show you the end result, right? I mean, okay, it probably took about 25 epochs or so to converge to get to the best performance, and in terms of loss and also in terms of accuracy. But you probably know accuracy is not the right metric for semantic segmentation. So I actually did intersection over union, but not for the whole thing, right? Then you don't know where you're going right or where you're going wrong. So in this case, for each of the class, as you can see, I got very good IOU values, like 90%, 95%, 96%, 90%, and the 62% is this tough to segment, regions. Okay, so this is the story. Now let's actually jump into the code and get started. Okay, now here is the code, and let me just give you a quick overview of the folder structure or the directory structure that we are dealing with. In fact, I started off with very large images. I wrote a little piece of code to break these images into smaller chunks of 128 by 128, because that's what my system can handle. Okay, if your system can handle 256, even better. But this is fine because my microstructure, I can see the whole thing even in 128 by 128. So if I go to images, you can see a lot of different things going on. This is what I mean by seeing things even in smaller patches. Okay, if you go too small of a patch, you may lose that context between different regions, different phases. So you cannot go too small in your patch sizes. Okay, so it always has to be larger than a typical field of view that captures everything. Okay, so that's exactly what I've done. In fact, I did both of my images and masks exactly at the same time, and you may not see anything here in masks, but if I open this and change my brightness and contrast to 0 to 3, sorry, then you should see something. Okay, let me zoom in a bit. Okay, there you go. So now you see 0 to 3, right? I mean 0, 1, 2, 3 here. If I look at the histogram, you should actually look at 1, 2. In fact, these values are 1, 2, 3, 4, not even 0. So sorry, let's redo this. Set 0 to 4. Oh, sorry. Set 0 to 4. Okay, there you go. Much better. This is how the masks actually look like, all of the masks. Now, how did I generate these masks? I already mentioned to you many times. Just go to www.APEER, APEER, okay, APEER.com, and then just you can load your data sets as like a TIFF stack or individual TIFF images, and you can just paint your pixels. This is a very laborious process, right? Or if you have someone else do the labeling for you, great. But the idea is you need to have labeled images, meaning every pixel must mean something. Okay, in this image, every pixel means something. There is a reason why I'm spending this much time, because you need to understand exactly what the goal is here, right? So let's go to 300% so you can see both at the same time. So there you go. So the image on the right hand side, corresponding mask on the left hand side. The value of 1 corresponds to this darkish area, value of 2 corresponds to this. In fact, it would be nice if you can just do 0, 1, 2, 3, right, instead of 1, 2, 3. In fact, later on we'll kind of convert that here. And the brightest regions are value of 4. So that's the idea. 4 classes to segment. And I have a whole bunch of images and a whole bunch of patches. Okay, so far 6 minutes into this, we haven't started anything, but we covered very important topics here. Okay, so this is my folder structure. Now let's get into the code. In the last tutorials, like 204, 205, 206, and 207, we did use units. Let me create a bit more space so you can see here. And for that, we created a separate file with our simple unit model. And it takes in your image height, width, and number of channels as input. And it builds this unit network for you. It compiles it using Atom Optimizer. Binary cross entropy again. Why binary cross entropy? Because it was only binary segmentation. Remember, output, the last layer has only one output. Well, why 1 if it's binary? Why not 2? Well, it's binary. And one output is the probability, because you see the activation is sigmoid. So if the probability is closer to 0, then it is one class. If the probability is closer to 1, then it's a different class, right? So that's what's going on here. Okay, so far so good. Again, almost 8 minutes into this, we are slowly getting there. Now let's look at the multi-unit model. What did I change from the original unit model? I added one extra input called number of classes. I defaulted that to 4, but you know, the input that goes into this function is number of classes. Why? Everything else is exactly the same. I'm not changing anything here. What I changed is, instead of one output, I put number of classes as my output. So if my number of classes is 4, this final layer is going to give me 4 outputs, 1 for each class. And I also changed my activation to softmax. Okay, again, multi-class in this case. So from sigmoid, I changed this to softmax. This is the other change. Another change that you don't have to make, but I did, is I just removed the compile part from here, because I'd like to compile it in the main code to see how it reacts to various loss functions and optimizers. So it makes it a bit easy for us to play with this code. In fact, I was experimenting with focal loss. Yeah, we'll get to that topic later on. But this is what you change in the model itself. Not much. Add the number of classes as part of your input to the function, and change the final layer to output 4 outputs and not just 1, because we are going to have 4 classes in this case. Now you probably know what we need to do, which is we need to structure our input data for training in a way that it takes in these 4. Again, we'll get there. Finally, we are there. Okay. So again, if you understand the regular unit, this is a small extension to the regular unit, although you may spend hours trying to figure out, if you haven't done this before, trying to figure out how to get your mask data or label data ready. Okay, so let's go ahead and start by importing our model that we just looked at, right? So what is that called? It's called multi-unit model, right? So let's start by importing that. Okay, so we are good. And then the regular standard libraries, you probably know why we are using this again. And now I'm going to define my size X and size Y as 128 because the patches I divided my image into, all my training images are this size. So 128 by 128, and I'm defining a global variable again called a number of classes as 4. Remember, we have 4 classes, right? So 4 classes there. And I'm reading these images just like the last time. All my images are in 128 patches images. All my masks are in the subdirectory called masks. And I'm using glob to walk through each of these and read the image as gray level. If you want, you can resize the images if they are not already 128. That's why I grayed out this. If you want, you can use that and append it, meaning at the end of this, I'll get a list of train images with all my images captured. Okay, this is basic Python, as you probably know. So after this, I should see, I think I have 1600 images. So I should see a list of 1600 images. And then I'll convert that into a NumPy array. Okay, so as you can see up here, I have a train images list of 1600 NumPy arrays. Let's convert this list into a NumPy array so it makes it easy for us to work with. So now you can see my train images array is 1600 images. Each image is 128 by 128, and they're all unsigned integer 8s, meaning we need to normalize them at some point. I could have normalized them in here, but we'll do it later. Okay, exactly the same thing for my masks. Okay, so let's go ahead and read the masks and convert that into a NumPy array. This is pretty much the same as what we have done for our 2D unit, okay, until this point. So let's wait a second here. Okay, there you go. It's done, and let's convert that into a NumPy array. Okay, now if you look at our train masks, okay, these values, if I just type, I believe, let's come down here and do np.unique, okay, and our train mask. What do we have? Is not defined. Masks. Sorry. So my values are 1, 2, 3, 4. It's okay if you leave it there. And the reason I added this part of the code is, for example, if you have different labels, you need to encode these labels into 0, 1, 2, 3. Now, when you do, for example, intersection over union, okay, using Keras, it assumes that your classes are 0, 1, 2, 3, right? So either I should have initially labeled my labels as 0, 1, 2, 3. Because I haven't done that, I'm fixing that issue here. Now, when you apply label encoder, the way it works is it only works on a single vector. But now I have it, 3 dimensions, right? I mean, I have 1600 by 128 by 128. So all I'm trying to do here is reshape it into single vector, encode the labels, and reshape back into original shape. Okay, this is what happens when you are not prepared initially. Okay, let's go ahead and run this label encoder, and we did this many times in the previous tutorials where we have done breast cancer data set where you have malignant and benign, right? So we changed that to 0 and 1. So pretty much the same type of structure. So now I'm extracting the shape. I have 1600, n equals to 1600, h is 128, w is 128, correct? And now let's go ahead and reshape this into a single vector. So now if you look at train masks reshaped, I have how many ever by 1. Okay, so 1 vector. So now I can do my label encoder fit transform onto this. So it transforms everything. It re-encodes everything. Okay, now if you look at encoded, now you can see instead of 3, it starts, I mean, these values look like 2, right? So it's almost like -1. I could have done -1 there. Okay, now let's go ahead and reshape this. So now I'm back to original, right? So train masks encoded original shape. So all of these steps to go from 333 and all of that stuff to 222 and everything. And the reason why I'm doing this is to make sure in case you start with colored labels, and when you import them as color, they have some weird, values. And this is a great way of actually encoding your labels. Okay, now let's go ahead and see what our unique values are. They should be 0, 1, 2, 3. I'm all good. Okay, so this entire step is optional because I want my labels to be 0, 1, 2, 3. That's pretty much it. Okay, next, our train images. If you look at our train images, it's 1600 by 128 by 128. I need to expand the dimensions by 1, add a at the end. So they are the so they have the right dimensions for my neural network, right? For my unit. And now I'm normalizing everything. I should have normalized while importing, but it doesn't matter. You can normalize at any point. So let's go ahead and normalize this. So all my unsigned integer 8s will become float 64. Again, step by step. Data handling is very important. So far, what did we do? Other than label encoder, nothing, no tricks, right? Now, if you look at the masks input, we have to do pretty much the same thing. If you look at train masks encoded original shape, it's 1600 by 128 by 128. So let's go ahead and expand the dimension. So it's 1600, 128, 128 by 1. There you go. We are all set. Okay. So this is my train masks input. Almost ready. Now let's actually get a subset of this. So what I'm trying to do here is I'm actually splitting this data set twice, because I don't want too much data, for training. Again, I added this for you guys. So in case you don't have high, good resources, GPUs and all that, you can actually take a subset of your data, test it out with various models and see which one, or various optimizers or loss functions, and see which one works for you. Okay, so let's go ahead and split the data or train images and masks into 10% for testing, 90% for training. Okay, that's exactly what we're doing right there. We did that. And now I'm splitting it again. All of these X1 and Y1, what I call them, I'm splitting them again. Again, this is completely optional. Splitting them again because now I want a much smaller subset for my training. Okay, X train and Y train. And I'm taking 80% of this. Again, optional. Okay, so far nothing. So now let's look at the class values in the data set, right? So again, we know that 0, 1, 2, 3. This is a sanity check. After you do this, is everything the way it's supposed to be? Okay, now comes the additional step that we haven't followed in regular unit, which is we have to convert this into categorical. Okay, remember when you do classification problems, multi-class classification, you're converting them into categorical, right? Is this a cat or a dog or a building or a barn or sunset? All of these, you convert those into categorical. So instead of classes 1, 2, 3, 4 or 0, 1, 2, 3, you have classes 1 all zeros, 1 all zeros for the first class, right? So this is basically one hot encoding in a way. So let's convert this into categorical. So if you look at train masks categorical, now you'll see, where is it? Train masks cat. Now you see I have 1152 images, each 128 by 128 with 4 in terms of number of categories, right? So this is what we mean by two categorical, okay? And now I'm reshaping this. Let's go ahead and Y train categorical. Okay, there you go. And why did I do? I took the train mask categorical, and then I'm just reshaping this to. This is again. I was testing with a different data set, and this step was required. But I don't see any reason why you need this for this. For this example, basically. So train masks categorical right there is 1152 images, 128 by 128 by 4, and my Y train categorical is equal to train masks categorical, basically. Okay, I'm not doing much of any tricks right there. Okay, I should actually drop that line. Now let's do exactly the same thing for test. Okay, and then testing. Okay, so where are we? Let's again one more time confirm what that everything is okay. Okay, so we have our Y test categorical, Y train categorical. Y test, we have 160 of these, 128 by 128 by 4. So you're all good now. That's it. Now you're all now you're all set. I'm not going to talk about this class weight yet, but actually let's cover this. Sorry. Now, if you look at our data set, we don't have all of the pixels equally separated. Like for example, do I still have this image open? This is important, so let me literally take another couple of minutes. Let's just open, adjust brightness contrast, set 0. No, this started at 1 to 4, right? There you go. Okay, so if you look at this, in this image, this white, whatever that class is, the white class is such a minority class. And next comes some of these. And this class with the value of 3, I have so much of it. This is completely imbalanced, right? This is not a balanced data set. So we need to balance this. And the best way to do that is by there is a method called class weight in scikit-learn utilities. We are going to apply that onto our data set, and we want it to be balanced. So what it's going to do, let's go ahead and run these lines. It's going to give us class weights automatically by looking at how many pixels, how many data points have a class, label of 0, class label of 1, class label of 2, and class label of 3. Based on that, it's going to give us class weights. And this is something you can define manually if you want, of course. So looks like, as you can see, the class number 0, 1.9 is the weight. We just saw that class number 3, we have so much of it. So it's actually multiplying that by 0.3, meaning, hey, come down, okay? Don't be that much. And the last class, you see the white one, the bright one, we don't have much of it. So it's actually multiplying that by almost a value of 10. So you have like a higher weight to this. So in a way, this is balancing different unbalanced data, and this can be very useful, okay, for you to include that as part of your training. We'll see that in a second. Okay, after that we just define our image height, width, and channels, which is nothing but 128 by 128 by 1. And let's go ahead and import our model. Remember, our model is multi-unit model, and we have to provide the number of classes as input, the image height, image width, the number of channels as input. Okay, and now let's go ahead and get the model. And once the model is imported, we need to compile it. Remember, we haven't compiled it here. You see, I haven't compiled it here. If you try to run this, fit this, it's going to say, hey, compile your model first. So let's go back. And how are we compiling? I'm using Atom as optimizer, categorical cross entropy, right? This is not binary. We are using sigmoid. This is multi-class, so categorical cross entropy. And metrics, I'm going to use accuracy. By the way, you can replace this with focal loss if you want, okay? Focal loss is supposed to better handle this unbalanced data, for example. Go ahead and try that. And metrics, you can use accuracy. You can use dice coefficient. Again, that's I'm hoping you know that stuff anyhow. Okay, let's go ahead and compile this. And now let's go ahead and print the summary. Okay, again, what tricks did we do? Basically, we got our mask data or Y values to categorical. So what goes in has a shape of number of images, image size, and number of classes. That's it. That's the only trick we have done. Okay, so as you can see, the input here is 128 by 128 by 1, right? Because these are grayscale images, and the output is going to be 128 by 128 by 4. It's going to return as 4 images, each for each class. Okay, now what? Let's go down. Now we can go ahead and fit this. And while fitting, I commented this part out. If you include class weight equal to class weights, now it's going to use the weights that we just calculated up there. Okay, so it's up to you whether I actually got very good results without or with. The result is pretty much the same. So, but it completely depends upon the problem. Okay, what your images. So go ahead and do this. And I already showed you the loss curves and the accuracy that I got when I did this. So let's calculate the other stuff. Okay, so now let me load that file again. So this is this is not that accurate. Oh, this is model.save. Sorry, let's not do that. In fact, let's go down a bit and load the weights, because like I just said, I've already done that. So let's go ahead and load the weights so we can pretend that we just did it. Okay, so we saved like 20-25 minutes right here. Okay, now that we got this, let's go ahead and calculate intersection over union. In fact, if you just calculate accuracy, let's do that. Oops, let's go ahead and do our accuracy. When you evaluate the accuracy, again, how do you do that? Your test and then your Y test. Okay, I think I did a mistake right here. This should be, yeah, I think that's okay. We got 95.9%. Okay, now let's go down to, where are we? Down here. Okay, so intersection over union. There are multiple ways to calculate this, and sorry for blanking out there for a second. I thought I made a mistake right there, but looks like everything is okay. If you find a mistake, let me know. But anyway, we got 96% of accuracy, but 96% of accuracy is amazing. But again, for semantic segmentation, it's intersection over union. Okay, that's exactly why we came down here. And first of all, predict. Why predict is basically your model.predict on your X-test data. There you go. And once you have that, what I'm trying to do is, this is important. When you look at your Y predict, it's going to give you probabilities. It's going to give you 128 by 128 by 4, right? For each of this, it's just a probability going from 0 to 1. We need to convert that into categorical, which is what we call argmax, right? I mean, you convert the probability into a maximum value within that, within that array. So there you go, argmax. So when you do that, now you, instead of probabilities, you get either 0 or 1, right? Basically, if you have 4 probabilities, 0.2, 0.2, 0.2, and 0.4, it would be 0, 0, 0, 1, because 0.4 wins. So it's argmax. Again, I'm explaining the basics, but argmax is basically, hey, what is the maximum in this list or in this array? Okay, and that maximum will become 1, everything else will become 0. That's what argmax is. Okay, explaining the basics, but it's important. Okay, now we can actually calculate IOU. There is in keras.metrics, there is something called mean IOU, so go ahead and import it. Number of classes, I think I redefined this, but that's okay. Number of classes is 4. And now let's calculate mean IOU on these, and there you go. And let's go ahead and print out. Okay, it's actually giving us a matrix of this is the confusion matrix, and we'll use that in a second. So the overall mean IOU is 85.68. Sorry, 84.68. That's not bad. For the type of images I'm working with, if I get 85% of pixels actually all matching, this is amazing. But what's doing good, what's doing bad, right? So here I'm actually taking each of these values here. This divided by all of these will give me the probability, the IOU for that class. That's exactly what I'm trying to print out down here. So let's go ahead and run these. So IOU for class 1, 90%. For class 2 is 62%, class 3 is 96%, and class 4 is 90%. And you probably already, again, I keep closing these images, you probably already know. In fact, yeah, let's go ahead and look at one image. There you go. And I really want you to understand these two. Okay, so if I go back to this image, you see this is class 3. We already saw that, right? Class 3, it's doing it that, in an excellent way. 96% of these pixels are matching. Yeah, of course, because that's an easy one to do. The last one is this bright one, and it's still doing pretty good. 90%. It's doing it pretty good because it's easy to segment bright regions against darker backgrounds. And this 90% is this black region. This is also easy to do because I have a lot of it. What I don't have a lot of is this type of clayishy region. Okay, it's these regions. I don't have much of it, and these are tough to segment against this type of background. That's why I'm getting only 62% of this. And if you really would like to increase the probability of this, then increase the weight for this class a bit more and decrease the weight of this class a bit, lower. And you will see very nice difference. Okay, instead of using the default weights, you should probably play with the weights that way. Okay, so let's go ahead and apply this to a few random images. Here I'm just loading a few random test images and plotting them in nice colorful jet color maps so we can easily see how the outputs look like. There you go, some random image. The background is easy to do, and these are pretty nice. Yeah, so let's go ahead and run this again. I'm a bit curious why the background there showed up in red, but maybe a labeling mistake there. But you see how you see these in yellow and that in red. This is in dark blue, and these regions with textured in this light blue shade. So the important point here is the testing label and the prediction on this image almost identical. So it's actually doing a great job, as you can see. This is why units are amazing. Yeah, this is why I love units. I mean, I think I'm getting very good results right there. Okay. Yeah. So this is, oh, I think if one class is not there, then I guess it's adjusting the jet scale from the other. That's why the images kind of, I mean, this is supposed to look in yellow, but since I'm mapping them in jet, I don't have like one of the other classes, so it's just showing this in this color. That's my assumption. But anyway, so after 30 minutes now, you have seen how we can actually use unit, the standard unit, extend it to multiclass, and change the way we supply our inputs, and that's pretty much it. Everything else is pretty much straightforward. Okay, in the next tutorial, let's actually take this trained model and apply it to large images and automate it for many large images and stack them together for a 3D data set. Again, this is not going to be a true 3D kernels because that requires a lot of computation. Look up 3D units. If I have time, I'll do those someday. But for now, let's do large images, stack them together in the next tutorial. Please stay tuned. Do not forget to hit subscribe button. Thank you very much.